Hello, welcome back. So we're gonna talk about another method which is called the support vector machine. And so what does it mean, the vector support machine? Right? So a support vector machine are a supervised learning models with associated learning algorithms that analyze the data used for classification and regression analysis. They analyze the large amount of data to identify the patterns from them. The support vector machine are based on the idea of finding the hyperplane that best divides a data set into two classes, as shown in the image below. So the goal is to, if we have a bunch of data, our goal is to separate them, like divide them using a linear equation if you're talking about a two-dimensional space, or a plane if you're talking about a three-dimensional space. So we could go into a further and do four-dimensional space, right? But we quite don't see that or can't visualize that in our world. So it's a little bit harder um, to do. I mean, technically, we do live in a fourth-dimensional space. The fourth dimension is time, but it's a little bit harder for us to be able to imagine that. Um, so for now, we're just gonna keep it simple. But the vector, but support vector machine is what it does. It just analyzes the data and tries to divide them. Just tries to figure out a straight line, a line or a plane that would divide them separately. Like there's not gonna be any element overlapping on top of the line or the plane. So that's the idea. So for example, here we have two types of data, right? And we were able to find a straight line that would separate them finally. Okay. So the goal of the support vector machine is to train a model that assigns new unseen objects into a particular category. So it achieves this by creating a linear partition of the feature space into two categories based on the features in the new unseen objects. Documents or emails, it places an object above or below the separation plane, leading to a categorization of spam or non-spam. This makes it an example of a non-probabilistic linear classifier. It is a non-probabilistic measure. The features in the new object fully determine the location in the feature space, and there's no stochastic element involved. So imagine that you are that kind of like, you are playing a game and you decide that whoever is on, you make a line between people and you say whoever's on this side of the line will be the good guys, and whoever's on the other side of the line will be the bad guys. So you kind of like, you divide the group. But if you're able to find a straight line that separates them finally, then you're gonna be able to classify them. And whoever is on your side, right, of the group, then those all gonna be part of the good guys. Whoever's on the other side will be the bad guys. So then that's how, whenever you take a new data and you need to make a prediction, that's how they do it. Whoever lands on the one side of the line will be classified as one type of group, and the other one will be the other one. So we'll see more examples. Support vector machines is a frontier that best segregate the two classes. A hyperplane line. Support vectors are the data points that lie closest to the decision surface of hyperplane. They are the data points most difficult to classify. They have a direct bearing on the optimal location of the decision surface. Support vectors are the data points nearest to the hyperplane. The points of the data set that, if removed, would alter the position of the dividing hyperplane. Because of this, they can be considered a critical element to the data set. So now the way we determine that line, the vector line, or the plane that separates this data, is by actually looking at the data. So some of those data points will be crucial for the implementation of that line, to be able to find that line, and some of them would not make a difference, right? So let's talk about the hyperplane. As a simple example, for a classification task with only two features, you can think of the hyperplane as a line that linearly separates the classified state of the data. For example, let's determine if the pictures are a dog or a cat. So that would be a two-dimensional space. There's only two options for the classification. And we're talking about so we want to classify them. So that's the output. There's two options, but we only have two features that we want to determine. For example, if they meow or they bark, so that would be one way. And then if they well, there would be another difference between a cat. If they can, I don't know, land on their feet, right? Then that will be a cat, right? And then if not, that they are dogs. So that be two features there, and then that will create, because there's only two features, it's going to create this two-dimensional space where we can classify the dog and the cat between the two of them by a line, a straight line. Intuitively, the further from the hyperplane our data points lie, the more confident we are that they have been correctly classified. We therefore want our data points to be as far away from the hyperplane as possible while still being on the correct set of it. So when new testing the data are added, whatever side of the hyperplane it lands will decide the class that we assign to it. So let me explain what that means. So for example, let's say that you have this data, and actually, yeah. So let's say you have this data. Our goal is to create, we could have done, let me show you. We could have done a line that is closer to the green one. We could have chosen that line instead of this one. But our goal is to be able to have our points as far as that line, as far to that line as possible. So as you can see, the points on the data on the green the green data, it is very close to that line. So it's not we're not actually succeeding in separating that green points to the green line, to this green line right here, to this one right here. So remember, our goal is to be able to have that line as far away from those points so that you can see a middle ground forms, which is right between the 2 points, the two data classifications. So one of the problems that we could reach in here is that what about if we cannot find a straight line? So data are rarely ever as clean as our simple example above. A data set will often look more like a jumble balls below which represent the linear non-separable data set. So for example here, let's say that we have this data and we want to separate the greens and the blue. How can we do it with a linear line? And that is not possible. We can't do that. So in order to be able to solve this problem, we could reach a different dimension. We can extend to a different dimension, and maybe there we can find something that would divide them fairly. So in order to classify the data set like the one above, it's necessary to move away from the second dimension into the third dimension view. Explaining this is easier with another simple example. Imagine that our two sets of color balls above are sitting on a sheet, and this sheet is lifted suddenly, launching the balls into the air. While the balls are up in the air, you use the sheet to separate them. This lifting of the ball represents the mapping of the data into the higher dimension. This is known as kernelling. So let me show you guys an example. So here, this is our data, the green one. So this is our two-dimensional space, and you can see we couldn't find a line that was separated so that we can have the blues and the greens on a different line, separated. So, but what about if we, instead of having like that, we look at them in a three-dimensional space? So there is probably a separation then of the blues and the greens. So now you can see that we create this plane that separates the blues and the greens. So everything above this plane, everything about this hyperplane will be considered blue, and everything on the bottom will consider to be green. So that will be a solution to be able to separate the data. Now, let's say that we have a three-dimensional space and we can't find that plane, then we have to move to the fourth dimension and so on until we find that separation. because we're now in the three-dimensional, our hyperplane can no longer be aligned. It must now be a plane as shown in the example above. The idea is that the data will continue to be mapped into the higher and higher dimensions until the hyperplane can be formed to segregate. And that's what practically what we do. We're gonna keep doing it until we reach that separation of the two data. Now, and you might be thinking, well, how is that even mathematically possible to talk about a dimension more than four, the fourth dimension, the fifth dimension, and what does it even mean, right? So in mathematics, we have actually talk about or define things that are more than just three dimensions or four dimensions. We talked about 10 atoms of a 10 dimension, 20 dimensions, 100 dimensions, and you could actually the math will follow. It doesn't matter how many dimensions you actually talked about. So in mathematics, even though we live in the world of the fourth dimension, right? Then well, maybe possibly more. Maybe we might not even see them, but we're not even realistic that they exist. But in mathematics, we can actually extend that concept of the three dimension to a fourth dimension, a fifth dimension, and all the math will follow. Okay. Um, how does it work? How can we identify the right hyperplane? In the support vector machine, it is easy to have a linear hyperplane between these two classes, but another burning question which arises is should we need to add this feature manually to have a hyperplane? For example, here we have all the elements are inside the circle will be red and everything outside will be a star. So it's support machine vector machine has a technique called the kernel trick. These are functions which take low dimensional input space and transform them into a higher dimensional space. It converts not separable problems to separable problems. This function are the kernels. So what this is saying is that we can uh, that the kernel trick, what it does, it elevates the number of dimensions to be able to find this hyperplane that separates the groups. That's practically what this is. It's practically a summary of what we just talked about before. It is mostly useful in a nonlinear separation problem. Simply put, it does some extremely complex data transformation, then finds out the process to separate the data based on the labels or the outputs you have defined. So this automatically changes. It has this automatically feature that allows you to change from one dimension to another one until it finds the correct separation. So that's something that we won't worry about it, but we just want to know what is going on. The computer will automatically can find a dimension, the number of kernel, not a kernel, right, but the number of dimensions that we need to be able to have so that we can separate the data that we have, the classification. And that's the end of that session. So we'll talk about the Python next.